In this video, we're going to look at composing matrix transformations. It sometimes happens that we want to combine matrix transformations by performing one transformation and then another. For example, let's say we wanted to first reflect a vector over the x1 axis and then rotate the result counterclockwise by 90 degrees. We saw in the last video how to construct the matrix A to perform each of these. And so the matrix A for the first transformation of reflecting over the x1 axis would be the matrix 1, 0, 0, -1. And if S is the transformation where we rotate 90 degrees counterclockwise, we might call the matrix for that B. And in this case, that would equal 0, 1, -1, 0. Just as a little refresher, sort of where do these come from? If we're thinking of reflecting over that x1 axis, then we want to know, kind of where do E1 and E2 get transformed. So if we're reflecting over the x1 axis, E1 doesn't move, so it just stays at 1, 0. E2 is going to reflect over that x1 axis and go down to 0, -1. So this would be T of E2. Same thing over here, the rotation by 90 degrees counterclockwise. E1 would actually go to the position that E2 started, and E2 would rotate over here. So we'd have T of E1 is 0, 1, T of E2 is -1, 0. But what if we wanted to perform one of these and then the other one? So we're essentially looking for the matrix for S of T of X. So we're composing S and T. And this is sometimes also written as S with this little sort of circle notation and then T of X. So this is S composed with T of X, S of T of X. And this tells us to reflect first, then rotate, because T is what we would do first, and that is our reflection transformation, and then we would do S. So if we're looking at these as matrices, T of X is AX, S of X is BX. So S of T of X would be, so to sort of perform T of X, this would be AX. And then to perform S of that, we would do B times the resulting vector, which is AX. So we would do B times the vector AX. And the sort of general idea here is that's going to lead to our matrix multiplication. So if T of X equals AX, S of X equals BX, then the composition S composed with T is the matrix transformation associated with the matrix B times A. So going back to the previous slide, kind of the point here is that B times AX is equivalent to B times A times X. We can kind of reassociate the parentheses for this matrix and matrix vector multiplication. And so this gives us kind of a really nice way of studying and interpreting matrix multiplication. It can be thought of as the composition of the transformations that correspond to each of these matrices. One point I want to make here is that the order matters. So S of T of X, we take X to AX, and then we multiply that by B to perform that S operation. So the associated matrix is B times A and not A times B. So even though we're sort of performing the operation, the transformation associated with the matrix A first, no, excuse me, yeah, the matrix A first, I should say, we write it as B times A. So not this A times B, it's not that like sort of left to right. So This is the first transformation. This is the second transformation. And so, hopefully this little diagram up here helps explain why that makes sense. Matrix transformations must be compatible if they are to be composed. So for example, if T goes from Rn to Rm, the output, T of x, is an m-dimensional vector. For S of T of x to make sense, S must accept vectors in Rm. This is exactly the same condition needed to multiply matrices. So if T of x is AX, S of x is BX, S of T of x is B times A times X. The number of columns of B must equal the number of rows of A. Another thing I want to point out here that we talked about earlier with matrix multiplication is the order in which we do things. So does this order matter? Consider the earlier example, but in the opposite order. So suppose instead of the reflection, then the rotation, we did the rotation first and then the reflection. And so we have our matrices. If we wanted to find the matrix for T of S of X, then we would multiply the matrices in this order. The result here would be a 2 by 2 matrix. In particular, it would be the matrix 0, -1, -1, 0. So this is the T of S of X. So this is, first rotate, then reflect. If we did it in the opposite order, like we saw earlier, just show that up here as well on the same slide. So let's say we wanted to switch the order around. The result here would be 0, 1, 1, 0. So this is our first reflect, then rotate. And the results are different. And so this is just, a reminder that matrix multiplication is not commutative. The order does in fact matter. And we see it playing out here in this application of matrix multiplication as a way to interpret compositions of transformations with their associated matrices. If we were to sort of think about this playing out geometrically, if we take a vector and then, so I'll just kind of draw a vector here. Let's call this vector v. If I first rotate it by 90 degrees, so this would be, s of v, and then I reflect it, I'm going to end up down here, t of s of v, versus if I were to draw a new graph over here, sort of do it in the opposite order. So maybe here's v. If I first reflect it, so this would be p of v, and then rotate it, sort of looks like I end up back where I started based on how I drew this, but that's okay. So, maybe we end up rotating by 90 degrees, sort of get back up here. This would be s of t of e. The point here is that these are very different. So the order does in fact matter, both if we're interpreting these as matrix multiplication. We already saw that order mattered, and here order matters. This question of does order matter really only makes sense when these are all compatible. So n by n matrices, for example, you can always define the switching of the order. And so, the order will matter in general. Right. So the general point here is that AB does not equal BA. The order of the transformations does in fact matter.